Good day, ladies and gentlemen. My name is Ogiamien. Welcome to another edition of Prometheus University. Today, we'll be going over the second part in our 9-part series on bending stress analysis and design. And in this second part, we'll be focusing on the moment of inertia. In the first part, in the 9-part series, we developed the basics of bending stress. We developed an intuitive feel for what goes on in the cross-section of a beam when we apply a bending moment to it. We developed the section modulus, which is a cross-sectional property. And that's to say that it's a function of the shape of the cross-section of the beam undergoing bending. The section modulus describes the distribution of bending stresses along the cross-section in the elastic range. And we showed in that video how that's also related to the moment of inertia. So you should watch the first video for the development of those ideas. But here we're going to focus on the moment of inertia, get an intuitive feel for what it is, see how it relates to bending, and see how the mathematics connects with the natural phenomenon that we're intuiting. We'll begin this by deconstructing the phrase moment of inertia. Two key terms there: moment and inertia. Inertia, we have a feel for. It is a property of matter which is proportional to its mass, and it gives it resistance to a change in motion. It makes it such that it doesn't want to move when it's standing still, and it doesn't want to change direction or change speed when it's moving. Now, without the application of an external force. Now, we can say more formally that inertia is a property of matter that gives it resistance to acceleration, i.e. change of motion, and that inertia is proportional to mass. Now, moment, on the other hand, has to do with rotation or rotational force or a torque. So the moment of inertia refers to rotational inertia, okay? Hence, it has to do with the resistance to rotating, right? So the moment of inertia is a measure of the resistance of an arrangement of masses to rotate about a given axis, is a way we can state it formally. Now, let's develop and investigate this idea further about an arrangement of masses and rotating about a given axis and the kind of resistance that the arrangement of masses offers to that rotation. Now, we can do this by running a couple of thought experiments. Let's consider an arrangement of masses, arrangement A, a simple arrangement made up of two balls of mass m connected with a massless rod, and there's a length associated with the distance between the balls, L1. And the task is to rotate this arrangement of masses about an axis which is midway between the balls. So we apply a torque, T1, and the task is to rotate this arrangement of masses about that axis represented by the red dot, midway between the balls. Well, let's consider another arrangement of masses. Same balls, mass m. However, the distance between the balls right now is much greater in arrangement B. L1 is much greater than, L2, is much greater than L1. But the task is still the same. We're going to place an axis right there in between the balls, and we're going to rotate it by applying a torque. The question is, which arrangement of masses requires more rotational force, more torque to rotate? Now, I think that with a bit of intuition and from our past experience, we can guess correctly that arrangement B offers more resistance to rotating. Therefore, it will require a greater torque to rotate than arrangement A. So we can say that T1 is less than T2. Well, let's investigate this further. Let's consider arrangement B if made up of the same masses with the same distance L1 between them, but we move the axis of rotation closer to one of the balls. Now what happens? Again, this is still a thought experiment. And I think that with just a bit of intuition, we can tell that arrangement B will require more torque to rotate than arrangement A. Again, we're developing an intuitive feel for this idea of an arrangement of masses rotating about a given axis, and what are the parameters that make it such that one arrangement offers more resistance than another arrangement, right? So in order to develop this with more mathematical generality or more mathematical precision, depending on how you look at it, we're going to imagine an arrangement of masses, a general arrangement of masses, and describe the kinetic energy of the system. Because again, if we can add a 0.4 to our series of facts here, is that resistance to rotational motion depends on the distribution of masses with respect to the axis of rotation. That's how close or how far away from the axis of rotation are the masses, right? And we know that moment of inertia is a measure of the resistance of an arrangement of masses to rotate about a given axis. And it comes out from a description of the kinetic energy of a rotating system. We'll do this step by step. So let's consider an arrangement of masses m1 through m6 with distances to the axis of rotation r1 through r6 respectively. And we're going to apply a torque and rotate this arrangement of masses and write out a description of its kinetic energy, the kinetic energy of the system. So we're talking kinetic energy, so we know it's half mv squared, right? And the kinetic energy of this system would just be a summation of the kinetic energy of each individual mass, right? So we'll have half m1 v1 squared plus half m2 v2 squared all the way through to half m6 v6 squared. And we can write this also in summation notation. However, it is important to note here that we're talking about rotational motion, hence the velocity which we're talking about has to be written in terms of rotational parameters. So let's segue here tangentially and do a quick refresher on uniform circular motion. So if we consider a circular path here, the red circular path, it has a couple of parameters associated with it. It has a radius and it has an angle swept by that radius. So let's call that the radius r, the angle swept by the radius delta theta. The distance of the path itself, let's call delta s. If we include time in this, whatever body is traveling through this path, we can get a velocity, right? So again, our goal is to write in the kinetic energy expression the velocity in terms of rotational parameters, since we're talking about rotational velocity. Okay, now the distance delta s we know is r times delta theta. Well, delta theta is written in terms of radians. The linear velocity v is the change in the distance divided by the change in time. So it's delta s over delta t. We can rewrite this, since we know that delta s is r theta, we can rewrite this as r delta theta divided by delta t. Now, angular velocity comes in. Angular velocity omega is the rate of change of angle with time, radians per second, degrees per second, right? Revolutions per minute, RPM. So that's delta theta divided by delta t. We notice here in our expression for linear velocity, r delta theta divided by delta t, we have angular velocity, delta theta over delta t. So we can rewrite our linear velocity expression as follows, as r times omega, right? So again, we're going to replace in our kinetic energy expression v with r omega. So we have here summation of m r omega squared rather than v squared. So we can tidy up this expression further by taking out the constants, putting out the constants to one side. Okay, so half is a constant, we put it to one side. The rotational motion we know is a constant. For the arrangement of masses rotating about an axis, they all have a constant angular velocity. Their velocities will change depending on how far they weigh or close they are to the center of rotation, the axis of rotation. But their angular velocity is the same, so that's a constant. Okay, so then we're going to replace the summation with an integral sign and go r squared dm, right? We've taken out the constants to one side, and we've rewritten the summation sign as an integral sign. Now, basically, this expression here, the integral of r squared dm, is the moment of inertia. That's called the mass moment of inertia. And again, it is in describing the kinetic energy of a particular system that we come up with this expression. Now, how is this related to bending? We will see here in a second. First of all, let's add a couple of items to our list of facts here. Item number 5 states that the mass moment of inertia, which we just derived, is the integral of r squared dm, where r is the distance from the axis of rotation to the masses, and dm represents the masses. Now note that in the expressing of the kinetic energy of a rotating system of masses, we are being able to tease out a more precise notion of how the resistance to rotational motion depends on the distribution of masses with respect to the axis of rotation. In the beginning, we developed an intuitive feeling for how different arrangements of masses offer up different resistance to rotation. But now we can say more precisely that if we were to double the distance from the axis of rotation to the mass, we would quadruple the resistance to rotational motion. And if we were to quadruple that distance r, then we will be increasing the resistance to rotational motion by 16 times, and so on and so on. Item number 6 states that area moment of inertia is equal to r squared dA, the integral of r squared dA. Now, the area moment of inertia is a modification of the mass moment of inertia, whereby dm, mass, is replaced by dA, area. So if we go back to item number 3, which tells us that moment of inertia, mass moment of inertia, is a measure of the resistance of an arrangement of masses to rotate about a given axis. The area moment of inertia is a measure of the resistance of an arrangement of area to rotate about a given axis. And it is the area moment of inertia that we are concerned with when we talk about bending and bending stresses. And the question that immediately arises is, well, how is this all related? How is bending related to area moment of inertia? Well, we can begin to show this by first stating and then demonstrating that bending has to do with the rotating of the cross-sectional area of a beam about its neutral axis. Okay? And since area moment of inertia tells us something about the resistance of an arrangement of area to rotate about a given axis, then it should tell us something about bending. And we'll take this step by step. Now let's consider this transparent beam here with a rectangular cross-section drawn out in red. And this purple line here is basically a reference point representing the vertical, and the green line represents the neutral axis of the beam. Now, the neutral axis is a very important concept in the description of bending and bending stresses. I would refer you to the first part of this series to brush up on the basics of bending stress if you need to. Now, the question is, what happens to the cross-sectional area of this beam when we apply a bending moment to it and it bends, basically? What happens to that cross-section? Well, below we have the bent beam, and we can see that the cross-sectional area has rotated about its neutral axis. It is rotated with respect to the vertical about the neutral axis, right? Now, all we have demonstrated so far is that bending has to do with the rotating of the cross-sectional area of the beam about its neutral axis. And since the moment of inertia, area moment of inertia, is a measure of the resistance of an arrangement of masses to rotate about a given axis, and since bending is the rotation of the cross-sectional area of a beam about the neutral axis, it follows that area moment of inertia should be able to tell us something about the resistance offered by a beam to bending based on its cross-sectional area, based on the arrangement of the cross-sectional area, basically based on how far away the area or close the area is to the axis of rotation. So a deeper beam offers more resistance to bending because the cross-sectional area of a deeper beam has more area spread out further from the neutral axis. Therefore, it has a larger moment of inertia. It has more resistance to rotating. And this resistance to rotating of the cross-sectional area translates into a resistance to bending. And this kind of resistance to bending is basically related to the bending stresses that beam will experience, right? So what we're going to do next is derive the moment of inertia for a rectangular cross-section, see how it is related to the section modulus, and tie it all together as promised in the first video. Okay, now we may already know that the rectangular moment of inertia is equal to BD cubed over 3, where B is the breadth and D is the depth. But basically, we're going to use this equation r squared dA, integral of r squared dA, to derive that very formula for the moment of inertia of a cross-section, of a rectangular cross-section. And we're going to relate it to the section modulus and see how it all ties in. We're going to see why bending stress is equal to m over the section modulus, or mc over I, where I is the moment of inertia. Well, first of all, let's draw this cross-section out and put some parameters to it. D for depth, B for breadth. The R axis here represents distance from the neutral axis. The neutral axis is the dotted line that goes through the center of the rectangle. Now, for a rectangular shape, the centroidal axis and the neutral axis are one and the same. So we have D over 2 above and D over 2 below the neutral axis. And we're just going to call C the distance to the neutral axis, which is equal to D over 2. And we'll see why that's important later, because in the equation MC over I, that C comes in. Now, basically, we're going to use this operation, integral of r squared dA, on this cross-sectional area which we just described. First of all, let's define dA. dA is a differential element of area, meaning a small, tiny element of area, and we represent that with that blue bar there, and it basically is B multiplied by dr, right? So we're going to rewrite our integral as the integral from negative d over 2 to d over 2, right? Because if you look at the axis, if the neutral axis represents 0, then we're going down from negative d over 2 to d over 2, and we're integrating b dr, right? R squared b dr, and b dr is dA. That's why it's in there. Now, if we do the operation, no need to go through too much of the algebra here, but we will end up with BD cubed over 12, right? And that's the moment of inertia of a rectangular cross-section. Now, we know that bending stress can be represented as the moment applied divided by the section modulus, and it's also written as MC over I. Therefore, the section modulus is equal to I over C, where I is the moment of inertia and C is the distance to the neutral axis. So we can demonstrate this by doing the simple math. Here we have, for the section modulus of a rectangular cross section, it's BD squared over 6, and we derived this in our first video. C is D over 2, therefore I over C is equal to BD squared over 6, right? Which is the section modulus. So now we've demonstrated why bending stress is equal to MC over I. It's basically because the section modulus is equal to I over C. Now, let's do a quick recap. I know this is a long video relatively, and there's many concepts in here. But basically, we have said that moment of inertia refers to rotational inertia. It's a measure of the resistance of an arrangement of masses to rotate about a given axis. We developed a more precise formulation for that by expressing the kinetic energy of a system of rotating masses. And we came up with the equation, or the formula, I should say, the integral of r squared dm. We said that in item number 6, the area moment of inertia modifies the mass moment of inertia by replacing mass with area. And we also went to demonstrate that bending has to do with the rotating of the cross-sectional area of the beam about the neutral axis. And since the area moment of inertia is a measure of the resistance of an arrangement of area to rotate about a given axis, it also can tell us about the resistance to bending offered by a beam, how a beam resists bending based on its cross-sectional area relative to the neutral axis, right? Thank you very much, ladies and gentlemen. If you enjoyed this video, please share it with your friends and subscribe to our YouTube page. This has been another session, another edition of Prometheus University. In the next session, we'll be going over elastic curvature of beams. Basically, we're going to be coming up with formulations that predict how much a beam should bend, how much should it deform and deflect under a given load. As we can imagine, the bending of a beam just doesn't have to do with the cross-sectional area. It also has something to do with the stiffness of the material, right? So we're going to use the stiffness of the material and the moment of inertia to come up with a formulation that describes and predicts how a beam should bend under a given loading. Thank you.